Wanted to work through a example of refraction of light rays. This one's actually a natural example of refraction of light rays. It's the refraction of sunlight when it enters the Earth's atmosphere. An interesting fact is that we see the sun before it rises above the horizon. And we also see the sun after it falls below the horizon. And reason we see the sun before it rises above the horizon and after it falls below the horizon is that light is refracted, sunlight is refracted at the Earth's atmosphere. And that refraction, bending of the light rays, that refraction, that deflection of the light rays allows us to see the sun when it's below the horizon, as it's just about to rise and as it's just about to set. So it's a small effect. It's not a very big effect. The effect is about 1 minute of extra sunlight before the sun rises above the horizon, 1 minute of extra sunlight after the sun falls below the horizon. But we're going to calculate that effect now we understand refraction. So I've sketched here, I made a sketch here that shows the Earth's surface in black. It shows the atmosphere's upper surface in blue. And then outside that is cold, dark, empty space. On the sketch, I've added a light ray that's coming from the sun. So I've imagined the sun is over here on the left. Obviously, in reality, it's very far over here on the left. But the light ray is coming towards the Earth. It strikes the Earth's atmosphere. That's a boundary between one medium and another medium, one optical medium and another optical medium, between empty space and the Earth's atmosphere. It's refracted according to the law of refraction. And so it's bent, deflected according to the law of refraction. You can see that it's refracted here in my sketch. And then here's the light ray traveling towards the surface of the Earth, where at this point here, I observe that light ray. I see that light ray. And so I'm seeing the sun before it's actually crossed the horizon. If I was to extrapolate this horizontal line, which is the horizon, back towards the left, the sun is below that horizontal line. I'm seeing the sun when it's below the horizon. And we're going to calculate how far below the horizon it is. What we'll do is calculate the number of degrees below the horizon, and then we'll turn that number of degrees below the horizon into how much time of extra sunlight we get. To solve this problem, there are two parts. The first part is a bit of geometry, right-angle triangle geometry. That's common in problems involving ray tracing. The second part is a little bit of understanding of reflection, refraction, in this case, refraction of the light ray at the atmosphere. So let's start with the geometry. I'm going to construct a triangle. It's this triangle here. So one side of the triangle upstairs here that's horizontal is the light ray that I'm seeing after being refracted from the Earth's atmosphere. A second side of the triangle is the vertical side here. That's just the radius of the Earth. So this is the Earth's center down here. And then the third side of the triangle, that's the hypotenuse of the triangle. That side is the longest side of the triangle. It has a length that is the Earth's radius plus the thickness of the atmosphere. Now, the Earth's radius is 6,370 kilometers. The thickness of the atmosphere is about 9 kilometers. So this side of the triangle is actually 6,379 kilometers. Now, I've not drawn this triangle to scale. It's a right angle triangle. There's a right angle here defined by the horizontal horizon and the radius of the Earth. This hypotenuse of the right angle triangle is only slightly larger than this side of the right angle triangle. So this angle at the bottom of the triangle is really very small. And this angle at the top of the triangle is really close to 90 degrees. And we can calculate this angle upstairs here using geometry, because we know two sides of the triangle. And this angle up here is actually the refracted angle of the light ray. It's the direction of the light as it emerges from refraction at the Earth, at the atmosphere's space boundary. That's because this side of the triangle, I drew it so that it was normal to the space-atmosphere boundary, space-atmosphere interface. So it's this line, this normal, with which we measure the direction of the refracted ray. So this is theta r. So given that understanding, let's calculate what theta r is, what that angle is in degrees. Sine of theta r, the refracted angle, is equal to the opposite side of the triangle divided by the hypotenuse of the triangle. So it's equal to, this is the opposite side of the triangle, the radius of the Earth, 6,370 kilometers, divided by the hypotenuse of the triangle, which is the radius of the Earth plus the thickness of the atmosphere. That was 6,379 kilometers. And so if I divide 6,370 by 6,379, I get a number that's very close to 1, but not exactly 1, just a little bit smaller than 1. It comes out to be 0.9986. I wrote it down. And if I take the inverse or arc sine of 0.9986 in degrees, I get an angle that is 87.0 degrees. And so that is the refracted angle. You see, it is indeed very close to 90 degrees. The angle in the bottom corner here will just be that 3 degrees that is missing. So we've already figured, just by basic geometry, the refracted angle. The next step in the problem, in solving the problem, is to figure out the incident angle. The incident angle at that space-atmosphere boundary. So let me just indicate that incident angle on the sketch is this angle here. So again, it's measured with respect to the normal, to the space-atmosphere boundary, and it's the direction of the incoming light ray with respect to that normal. So this is theta I. To calculate that, we can use Snell's law of refraction. We know the refracted angle. We want to figure out the incident angle. And also, we know the refractive indices of the two media. Let me write them down here. So one of them, I call it Ni, the incident medium. That's outer space. That is vacuum. That's empty space. That is a refractive index of 1. The other one is the air in our atmosphere. And the air in our atmosphere has a refractive index that's 1.003. And so we know the two refractive indices, we know the refracted angle, we can figure out the incident angle. Let me write down Snell's law. Ni sine theta I equals Nr sine theta r. Remember, it is the product of the refractive indices and the sines of the angles being the directions of the light rays in the two different media, the incident medium and the refractive medium. Those products must be equal to one another. In our case, we want sine theta I. And so I can just divide through by Ni. Ni is just 1, in fact, and I can fill in the numbers. I've got for the refractive index of the air, 1.0003, for the sine of the refractive index, refracted direction, angle of refraction, I've got the sine of 87.0 degrees. And if I do this calculation, I get the, and then take the inverse of this, the sine or the arc sine, I get an angle that is 87.3 degrees. And so we see now at this point, we step back from the problem and think about where we are in this problem. We've calculated the refracted angle, 87.0 degrees. We've calculated the incident angle, 87.3 degrees. There's a small deflection of the light ray. We can see it in the sketch as it traverses the space-atmosphere boundary. That small deflection of the light ray is what we need to figure out the extra sunlight, the extra time that we see the sun below the horizon before it's about to rise, or also below the horizon after it's set. So let's calculate this, this deflection angle, I'll call it, delta. It's simply the difference between the incident angle and the refracted angle, because they're both measured with respect to the same line, the normal. And so this is going to be 87.3 degrees minus 87.0 degrees. I won't write down those two numbers. This is just 0.3 degrees. And so that is the angle below the horizon at which we first see the sun, 0.3 degrees. It's the angle below the horizon that we last see the sun at sunset, is 0.3 degrees. Well, so finally, how much extra sunlight do I see before the sun rises physically above the horizon? How much extra sunlight do I see before the sun, after the sun falls physically below the horizon? Let's figure that out. To do that, all we got to do is realize, look, we're seeing an extra 0.3 of a degree at sunrise, an extra 0.3 of a degree at sunset, out of a total 360 degrees of the sun's travel around the Earth in this sketch. And so if I was to divide 0.3 degrees by 360 degrees, that's the fraction of extra sunlight that I'm getting at sunrise or at sunset. If I multiply that by 1 day or 24 hours, that's going to be the extra time that I see the sun at sunset, sunrise. So if I calculate 0.3 degrees divided by 360 degrees, it's about a part in 1,000. I end up with a calculation that tells me I get an extra 1.2 minutes of sunlight at sunrise and 1.2 minutes of extra sunlight at sunset due to the refraction, the bending of the sun's rays as they enter the Earth's atmosphere. Anyway, this was an example of refraction. It was a problem involving refraction. It was a natural example of a problem involving refraction. Like many problems in optics, ray tracing, we had to do a bit of geometry. We also had to use either laws of refraction or laws of reflection or both. This case was just refraction. But it is a nice example, a nice illustration, a nice application of Snell's law to understanding a natural phenomenon.